rounding off numbers according to sig figs. So per sig figs, which we will call s.f, okay, for the remainder of this video. So let's switch colors here. We're going to call this we need 3 sig figs here, okay? And the number is 26.142, okay? So we have 1, 2, 3 sig figs to 26.1. The 4 is not 5 or greater, okay? And this is the 5 rule. So the 4 is the first one we're going to drop off. We see that. That's the first number, the first digit to drop off. And because it's not 5 or greater, the number directly to the left of it will remain the same. Now, had it been 5 or greater, the number, or excuse me, the digit to the left of it would move up by 1 numeric value. So it'd be 26.2. But because 4 is not 5 or greater, we call it 26.1, and we get all 3 sig figs, okay? So now, let's clear this out and do another one. So we're going to do, again, 3 significant figures, and this time we're going to do 10.063, okay? And we're going for 3 sig figs, okay, for 10.63. So, 1, 2, 3. Now, these are what we call captive zeros, meaning that there are digits greater than 0 on both sides, okay? So they are considered sig figs. They are considered sig figs because they're captive between digits greater than 0. So, 1, 2, 3, 6 is the first number to drop off, and we ask ourselves, is that greater than 5 or greater? And it is. So the digit, directly to the left of it will increase by one value. So we have 10.1, and we have 3 sig figs, and we have rounded correctly. Now, the next one is kind of an important one that you hear, because it sometimes confuses people. So we're going to try and make this really, really simple. So we have 0.0997, okay? And we're going to go 2 sig figs, okay? 2 sig figs. So now, you might think 1, 2. But the thing that you need to understand is these zeros are not captive. These zeros, if there was a digit over here greater than 0, we would have captive zeros, but there isn't. So they don't have value except to identify the decimal place value. That's the only purpose they serve. So we don't count them. So it's actually 1, 2. So the first number to get dropped off is going to be this 7, which is, of course, greater than 5. So the digit directly to the left is going to increase by 1. So it becomes 0.10. So we see as we round up, we end up with 0.10. And again, this 0 is not significant because there's no digit next to it greater than 0. So we have 0.10 gives us 2 sig figs. Now, the last example that we're going to cover with regard to rounding and sig figs is the result of the product of a measured number, measured numbers, 5.0 times 356 equals out to 1,780, okay? So because the result should have only 2 significant figures as limited by the 5.0, we round off 1780 to 1800. Now, this gives us the perfect opportunity to, let's rewrite that as 5.0 times 356 equals 1,780, which rounds to 1,800. Now, this leads us into something called powers of 10 notation or scientific notation. So we could say that we could rewrite this 1,800 as these numbers get really, really big in science, like physics and chemistry, dealing with moles, where we have this massive number or this massively small number with huge decimal places. We can use this scientific notation. So we have like 1.8 here times 10 to the third. And that third is just telling us we're going to go 1, 2, 3. See, let's look at that. So we have 1.8 times 10 to the third equals 1.8. And that third tells us, because it's 10 to the third, it's just telling us we're going to move that decimal place three places, right? We're just going to go 1, 2, 3. And look what that comes out to, 1,800. 1,800.0, right? Okay. And we can see that that's 2 sig figs because we talked about those zeros, right? So we have 1,800. It's 2 sig figs, actually. There we go. Especially because we're going to write it in scientific notation, 1.8 times 10 to the third. And we're going to talk more about scientific notation as we move on in this physics course. So I hope that made things a little bit clearer. I'm trying to think if there's anything that we could have covered that we didn't, and I think we got most of it. Let me just show you an example. So like 10 to the second would equal, right? That's 10 squared, so 10 times 10, which equals 100, right? Right? We remember that. So 10 to the third is going to equal a 10 with 3 zeros, which is 1,000, right? So when we're looking at 1.8, we're like, well, it was 1,800, so it was 1,800. So we're just going to say, well, how many digits are to the left of that decimal, okay? How many are we supposed to have? Okay, so if we're supposed to say we're supposed to have 3, we just do times 10 to the third. If we're supposed to have 2, we would do times 10 to the second. If we're supposed to have 4, we go 10 to the fourth, right? based off this guy right here, because that's how many places we're going to move that decimal. And that's what this is all about right here, this power of 10 notation. So if I said 10 to the 4th, it's going to equal a 1 with 1, 2, 3, 4 zeros, right? Which is 10,000. Right? So if it had been 18,000 that we had to get to, it would have been 1.8 times 10 to the 4th. And then if we need to get the decimal place moving this direction, we do the same thing, but we'd say negative 4th. That's really all we're doing. So when we have these huge numbers, so let's say 18 with 1, 2, 3, 4, 5 zeros after it, right? So we got, let's see, 1,800,000. So we're going to have to move that decimal 1, 2, 3, 4, 5, 6 places. So it'd be 1.8 times 10 to the 6. It's just a faster way to write that and a simpler way to write that. Because these numbers can get very large, okay? When we start talking about in physics, like things to the power of negative 23 or something like that, that's a huge number to write out. So we write it out in the scientific notation or power of 10 notation. All right, good deal.